Hi, I am John Ray M. Perez, and I'm going to discuss about the measurement of precipitation and rain gauge network. First off, the measurement of precipitation. What are the things we are going to measure? The first one is rainfall. The amount of precipitation usually measured by the depth in inches. The second is snowfall. Snowfall as a form of precipitation differs from rainfall in that it may accumulate over a surface for some time before it melts and causes runoff. Continuing in measurement of precipitation, a rain gauge is a device used to collect and measure precipitation, essentially consists of a cylindrical vessel assembly kept in the open to collect rain. The rainfall catch of the rain gauge is affected by its exposure condition. To enable the catch of the rain gauge to accurately represent the rainfall in the area surrounding the rain gauge, settings are adopted. The following considerations are important in setting the rain gauge. The ground must be level and in the open, and the instrument must present a horizontal catch surface. The gauge must be set as near as the ground as possible to reduce wind effects but must be sufficiently high to prevent splashing, flooding, and etc. The instrument must be surrounded by an open fenced area, at least 5.5 meter. No object should be nearer to the instrument than 30 meter of twice the height of the obstruction. Rain gauge is classified into two, the non-recording gauges and the recording gauges. Recording gauges produces a continuous plot of rainfall against time and provide valuable data. There are four commonly types of recording gauges, which are the tipping bucket type, weighing bucket type, natural siphon type, and telemetering ring gauges. While on the other hand, the non-recording gauges was usually extensively used in India. The non-recording gauges The non-recording gauges extensively used in India is the Simon's gauge. It essentially consists of a circular collecting area of 12.7 cm or 5-inch diameter, connected to a funnel. The rim of the collector is set in a horizontal plane at a height of 30.5 cm above the ground level. The funnel discharges the rainfall catch into a receiving vessel. The funnel and the receiving vessel are housed in a metallic container. Water contained in the receiving vessel is measured by a suitably graduated measuring glass with an accuracy at 2.01 mm. This rain gauge can be also used in measuring snowfall. So for the next type of recording gauge is the tipping bucket type and the weighing bucket type. The tipping bucket type consists of a funnel that collects and channels the precipitation into a small seesaw-like container, while the weighing bucket type is a self-recording rain gauge. It consists of a receiver bucket supported by a spring or lever balance or some other weighing mechanism. The movement of bucket, due to its increasing weight, is transmitted to a pen, which traces record or some marking on a clock-driven chart. Next one is the natural siphon type. It is also known as a flow type gauge. The rainfall is collected by a funnel-shaped collector leading into the float chamber, causing a float to rise. As the float rises, a pen attached to the float through a lever system records the elevation of the float on a rotating drum driven by a clockwork mechanism. On the figure, A typical chart from this type of rain gauge. This chart shows a rainfall of 53.8 mm in 30 hours. The vertical lines in the bent trace correspond to the sudden emptying of the float chamber by siphon action, which reset the pen to the zero level. The next one is the telemetry rain gauge. These rain gauges are of the recording type and contain electronic units to transmit the data on the rainfall to a base station both at the regular intervals and on interrogation. Telemetry gauges are of utmost use in gathering rainfall data from mountainous and generally inaccessible places. So the next one is the radar measurement of rainfall. The meteorological radar is a powerful instrument for measuring the areal extent, location, and movement of rainstorms. Further, the amounts of rainfall over large areas can be determined through the radar with a good degree of accuracy. The radar emits a regular succession of pulses of electromagnetic radiation in a narrow beam. When raindrops intercept a radar beam, it has been shown that P sub r is equal to Cz over r squared, whereas Pr is the average echo power, Z is a radar echo factor, r is a distance to a target volume, and C is a constant. Generally, the factor Z is related to intensity of rainfall, as Z is equal to A times I raised to B, where A and B are coefficients and I is the intensity of rainfall in millimeter per hour. The values A and B for a given radar stations have, the, have to be determined by a calibration with the help of recording rain gauges. A typical equation for Z is equal to 200 I raised to 1.16. A meteorological radar operates with wavelength ranging from 3 to 10 cm, the common values being 5 and 10 cm. For observing details of a heavy flood producing rain, a 10 cm radar is used, while for a light rain and a snow, a 5 cm radar is used. So for the next one we are going to measure is the snowfall. It is a form of precipitation that differs from a rainfall. It can accumulate over a surface for some time before it melts and causes up. The evaporation of the surface of accumulated snowfall is a factor to be considered in analysis dealing with snow. For the depth of the snowfall, it is an important indicator for many engineering applications, and in hydrology, it is useful for seasonal precipitation and long-term runoff forecasts. The water equivalent of a snow. The depth of water that would result in melting unit of snow. This parameter is important in assessing the seasonal water resources of a catchment, as well as in estimates of a stream flow and floods due to a melting snow. The amount of water present in a known depth of snow can be estimated if the density of the snow is known. The density of a snow varies considerably. The freshly fallen snow has a density in the range of 0.07 to 0.15, with the average of 0.1. But with the accumulated snow, it causes a high density that it may range into 0.4 to 0.6. Wherever specific data is not available, it is safe to assume that the density of the snow is 0.1, which is the same as the fresh fallen snow. The water equivalent of snow can be obtained in two ways, using snow gauge and snow tube. In snow gauge, a receptacles to catch precipitation as it falls in a specified mapling area. Snow tube is a set of a telescopic metal tubes, a tub size of 40 mm or 90 mm. The main tube is provided with a cutter edge for easy penetration, as well as to enable extracting of a core sample. Raingauge network. Since the catching area of a rain gauge is very small compared to the extent of a storm, it is obvious that to get a representative picture of a storm over a catchment, the number of rain gauges should be as large as possible. The catchment area per gauge should be small. Economic consideration to a large extent and other consideration such as topography, accessibility to some extent restrict the number of gauges to be maintained. Hence, one aims at an optimum density of gauges from which reasonably accurate information about the storms can be obtained. Toward this, the World Meteorological Organization or WMO recommends the following density. For flat regions of temperate Mediterranean and tropical zone, the ideal is one station for 600 to 900 kilometer square, but the accept but the acceptable is one station for 900 to 3000 square kilometers. For mountainous regions of temperate Mediterranean and tropical zone, the ideal is one station for 100 to 250 square kilometers, but the acceptable is a one station for 25 to 1000 square kilometers, and for arid and polar zones, one station for 1500 to 10,000 kilometers squared. 10% of rain gauge stations should be equipped with self-recording gauges to know the intensities of rainfall. From a practical consideration of engine conditions, the engine standard recommends the following. In plain, one station per 520 kilometers squared. In regions of average elevation, 1000 meter, one station per 260 to 390 square kilometers. In predominantly hilly areas with a heavy rainfall, one station per 130 square kilometers. Adequacy of a rain gauge station. If there are already some rain gauge in a catchment, the optimal number of stations that should exist to have an assigned percentage of error in the estimation of mean rainfall is obtained by statistical analysis as per so in the equation. N is the optimal number of stations and E is the allowable degree of error in the estimate of rainfall, while CV is the coefficient of variation of the rainfall values at existing M station. If there are M stations in the catchment, each recording rainfall values P1, P2 until PM in a known time, the coefficient of variation is calculated as, for example, a catchment has a 6 rain gauge stations. In a year, the annual rainfall recorded by the gauges are as follows. For a 10% error in the estimation of the mean rainfall, calculate the optimum number of stations in the catchment. Oh, the coefficient of variation is equal to 100 times 35.04 over 118.0 will lead to 29.54. Calculate again 29.54 over 10 squared is equal to 8.7. Generally, there, we can say that there are 9 stations. Thank you.